Once again, hello. Thank you for coming. I'll continue my presentation about. We continue our study of curves. Today we're going to just discuss a little bit derivatives of curves, which is the easiest setting of the derivatives for different functions. Remember, last time when we discussed our object of study, I told you that we have lots of different combinations of domains and codomains of the functions when we study them, lots of different combinations of dimensions of the domain and codomain. Curves, they represent relatively simple setting when you have the only one variable in the domain and n variables in the codomain. That's why we start with this setting. And the derivative, in particular, relatively easy here. So from definition point of view, derivative doesn't really bring any surprises. So we just say the function is differentiable at a point. It's a formal definition of it. When we have a limit of this type, the one which you see on display, when you have such limit, when such limit exists, okay? And of course, when I say limit right now, we understand limit in terms of components definition, in terms of this simplistic definition I introduced 2 days ago. Later on, tomorrow, the day after tomorrow, we will just discuss limits a bit further, and I'll present you a different definition of limit, more general one, which works not only for curves, but any other function. And later on, when it comes to derivatives, again, the same definition for the derivative of the curve will be applicable, even just with one alteration. We will change the way we interpret the lim symbol, because today or tomorrow and the day after tomorrow we're going to discuss limits, another definition of limits. Normally you have a notation for this limit. If it exists, that's how you denote it. You call the derivative of a function at the point f dash of a. That's the symbol for that. And that's just a development of the definition. You say f is differentiable on the entire interval if it is differentiable in every point. It's just regular development of a definition. You have to get used to this sort of way of stating things. First, you define something at a point, and then you define something across the interval by claiming it's true at every point of the interval. If you have a function which is given by components, if you have your vector function given by component functions which are numerical functions, the first result which we have to keep in mind all the time, if I differentiate a function, function is differentiable in the sense of this definition, if and only if it is different, every component is differentiable individually, and derivative will be equal to the combination of or collection of derivative of components. Quite expectable result, especially given our definition of a limit, which was defined as a per component limit. That's the first thing you have to keep in mind. That's actually very similar to the result we discussed 2 days ago about the continuity. When we remember, there was a result, there was a theorem there which said function is vector function, curve is continuous when every component is continuous individually. For that theorem, I didn't show you the proof, even though if you check Moodle recently, I uploaded the notes of the proof on the website. For this one, I'll show you the proof because the argument is similar. You can develop the argument I'm going to show for this theorem, for the theorem on continuity. So let's just look at the proof of this theorem. We have 2 proofs today to look, and on the proof side, I'm planning to present 2 proofs today, so it's one of them. It's coming right now. Let's just do it here again. I don't understand. It doesn't matter. It doesn't give me the full screen, but it doesn't matter. Here it is. Derivative per component theorem. I will open this is my slide. I'll zoom it in a little bit. Just wait a sec. The other way. Yeah, that's better. Derivative in case of components. So here's my setting. I have function, which is given on the interval. Function given by components. It's the same setting you saw on the other slide. each of these components individual functions, numerical functions. So the theorem we're discussing, as the theorem which you saw already, just repeating the statement on this slide again, we say that the function f is differentiable at some point if and only if every component xi, every component is differentiable at the same point, at the same point A. Furthermore, the theorem claims that the derivative of this vector function will be a combination of derivatives of individual components. Proof. Given that the statement of the theorem has this if and only if part, I don't know if you know this abbreviation IFF normally it means if and only if. That's how you can interpret this. Well, that's how we interpret this. Every proof of every statement like that will have two parts. Forward part, when you prove that the f being differentiable implies that every component is differentiable, and the opposite part, where every component being differentiable implies that the f as a whole is also differentiable. So my forward path, the forward part of the proof, it goes like this. It's a simple proof. Mathematically, it doesn't represent any challenge, but presentation-wise, it may be a challenge for some of you. So here's how you can do it. One way to do it. So given that f is differentiable, we just use the definition to just expand this assumption. F is differentiable means that the limit like that exists. I just use the definition for the interpretation of f being differentiable claim. Now, I'll move it a little bit here. If I compute this vector, it's a vector, right? F bold is a vector, f of t is a vector, f of a is a vector. If I compute this vector, it will be relatively large expression. Here it is. Let me just, I can't move it anymore. Here it is. First component, dots hiding most of the components, and the last components of this expression. Given this algebraic formula, you see my f given by components. So if I compute the quotient of this vector function, that will be the components of my quotient. By definition of the limit, remember we define the limit as we define the limit in a per component sense. So when we claim that something like this exists, it just underneath it means that every component limit exists. So by the definition of the limit, every component limit exists, like this. And you see, I used my trick. I used the I index to sort of mention every component rather than saying x1, x2, xn. I just use the I index. So from here we can say when such a limit exists, we know it from the elementary or from the numerical calculus of the first year calculus that it means that xi function as a numerical function differentiable, we know it from the first year at the point A. Furthermore, we can say that this limit basically has a name right now. It has the name x dash I at the point A. That's how we define the derivative of the numerical function. And so we can replace, if you put the limit here, if you put the limit symbol here, which means you put the limit here, second component, last component, every of these limits, we know they exist and we can abbreviate them with this symbol. We conclude that the f dash a, which is by definition this limit, is a combination of x dash 1, x dash 2, and x dash a. Yeah. Well, like I said, the proof itself mathematically doesn't represent any challenge. What you have to keep in mind and what you have to pay attention to is you just have to make a proper references at every step of your argument. For instance, this implication, that's the interpretation of the definition of f being differentiable. Limit exists. The claim that this exists comes from the fact that that's a definition of the limit of a vector function, because limit of a vector function exists when every component limit exists. This claim comes from the reference to the first year material, because when such a limit exists for numerical function, that's how we define the differentiable numerical function, and that's what that's the symbol which we use, and that's all the reference you have to make in this argument. Oh, yeah. Any questions? Okay. If you don't have any questions, I have a second proof to discuss with you. It's in line with what was 2 days ago in relation to the continuous functions. I need to go back to my main set of slides. No questions in relation to this? Okay, let's go back to the main set of slides. Was there any questions? Was something wrong?
I think you might not have finished the proof. I think it's an if and only ifs.
Ah, yeah, well, well, I sort of finished it, because on this slide, well, you see, okay, I did.
There we go.
Yeah.
Okay.
Well, actually, it is actually similar. You just have to reverse every implication in this chain of lines in the opposite order, right? You just, by assuming that every individual component is differentiable, you assume that every such limit exists. So you replace every component here with such a limit. And now when you know that every such limit exists, by the definition of the limit of the vector function, it means that the limit of the vector function exists. And that's why f is differentiable. So as a matter of fact, this if and only if, it's basically you can drag it all across these lines. There isn't much of a difference between one direction and the other direction. But thank you for mentioning that, yes. That's right.
Can you do like f is differentiable if and only if that limit exists, and you just go if and only if all the way through?
Yes, you can. Again, actually, now I realize I could have put it this way. That probably saved me this one extra line when I say the other part is similar. Yes, that's right. You can make this if and only if.
Like all the way through.
So, yeah, well, probably you have to change the wording a little bit in your presentation, but it's doable. You can try to think the structure of this presentation, and you probably can do it. Yeah. Yes.
So similarly, if I have finished the first group like this, then like while I'm writing like for assignment, for example, and then I'm trying to prove the only if part. Can I describe the only if can be proven because each and every step before is reversible. Kind of say that, and that completes the proof.
In this case, if you say so, we will accept that. Yeah, because it's relatively obvious here. Yeah. Yeah. I mean, if I can see that you can make this presentation forward, I'll be absolutely sure that you can make the reverse one as well. So if you just put this extra sentence saying that you can reverse every implication in this chain, that will be good enough for me. Any more questions? Okay, let's just look at the other one. The second proof, which I plan to discuss with you today, it's also in relation to the derivatives, and there is a similar question in the tutorial set, which will, I mean, you haven't seen the tutorial set yet, but you will soon. It's the other one which is quite expectable. You know, well, from your experience with the numerical functions, you know it relatively well. It says this: if you have, well, in this setting, if you have three functions, two of them vector functions, f and g, and one of them numerical function, lambda. If you have such three functions, and if you assume that three of them differentiable in their respective sense, f and g in a vector sense, lambda in a numerical sense, if you do algebraic combinations, and that's not all, this is not all possible combinations, of course, but I just chose three, well, the most common one. Like if you add two functions, if you scale a function, vector function by numerical function, if you dot product two vector functions, again, it's the same dot here and here, but it's essentially this is two different multiplications. One of them is a scaling, the other one is a dot product. All of these combinations will be differentiable in their own turn. Well, I have a proof for this theorem as well. It's another relatively routine proof. and I'm hoping it will be the last one, routine one, but I need to present a few routine proofs for you to have some benchmark when you're going to present your routine proofs. Okay? This is another relatively routine. I mean, mathematically, this doesn't represent any challenge. Representation-wise, it might be a challenge. That's why I'm going to do it again. We will we'll see how, I don't know, I'll try. There will be more challenging proofs later, obviously. Yeah, let's just look at the proof of this one. Yeah, here it is. Well, on the technical side, because we meet together in 3 different rooms, and these different rooms, they have different projectors with different resolutions. That's why the zoom originally doesn't set right. That's why I have to play with this like this, but it should be fine. So here's my setting again. I have 3 functions as before. 2 vector functions, 1 numerical one. The theorem claims this: if you have 3 functions originally differentiable in their respective sense, at some point, then if you combine them, then they will be differentiable at the same point, again in their respective, well actually in this case it will be all the time vector sense, because all of these combinations, no, wait a sec, my fault, no, not all of these combinations are vector functions. First one is a vector function, second one is a numerical function, because dot product returns number, last one is a vector function. And actually the theorem has a second part, which is not on my main slide. Not only you can claim that you know these 3 will be differentiable, you also can produce a formulae for the derivative, something you also know very well. For instance, the derivative of a sum will be sum of the individual derivatives. Derivative of the dot product, it's the same, it's something resembles a lot the product of numerical functions, even though, remember, this dot is a dot product, this dot is a dot product, and this dot is also dot product. And the scaling, again, similar formula, even though dot this time represent different multiplication. As far as, my notes tell me that I proved, on the slide, I have the argument only for one part. I think I chose the hardest one, the second one. The other 2, which are easier one, I left it just for you to play with. So let's just try to look into this on the slide. Here's the proof. So again, because everything happens by component, because our limits are defined in the per component sense, we need some names for the components of the vector function f and g. And that's what I'm going to do. I'm going to introduce the name for the components. x1, x2, xn will be the names, numerical functions of the components of f. And y will be the names for the g. Since f and g differentiable, every component of f and g is differentiable. Why is that? That's right. The proper reference at this place will be it's a per component differentiation, which we proved in the slide before. Well, I said by algebraic theorem. It's obviously it's a wrong one. It's a wrong reference. I just mistyped it. It's supposed to be by per component theorem. I just loosely call it like that. So, furthermore, again from this per component theorem, I know that the derivative of f and g, they will be like this. So let me just check it now. consequently, we compute the left-hand side here. If I compute the left-hand side here, look what it is. Here's the left-hand side. It's a dot product of f and g function. Because individually, every x1, y1, xn, and yn, they are differentiable. Their combination, their linear combination like this, it's numerical functions. It also will be differentiable. It's here. This combination is differentiable as a combination of differentiable functions, as a combination of differentiable and numerical functions. Yeah. So when I differentiate this, just this dash, by the way, this dash which sits here, it's a derivative of a numerical function because f dot g, it's a numerical function. So you apply this derivative to this long combination like this. But all of this is a numerical differentiation. We all know how to do that. It's the first year stuff. So when I differentiate this, and that's the way to write this, we differentiate this at the point A. See, you put this vertical bar and you indicate the point at which you differentiate that. We can use, this is the point where we reference the material from the first year because this is numerical functions. We can use the properties of the differentiation from the first year. We can say, first, we can drag this dash to every summed in this sum. And then, because it's a product of numerical functions, we can use the formula for the differentiation of the product of numerical functions, which is derivative of the first factor times the second factor, and then first factor times the derivative of the second factor. And that's exactly what's happening here. I drag my dash, this dash, to the first term and differentiate that. Derivative of the first times the second, first times the derivative of the second. And then for all of the components hidden by the dots, and for the last component, that's how the expansion will be. If you now rearrange it a little bit, if you combine this with this, I mean all first ones together and all second ones together, here it is. If you rearrange this now, this is the rearrangement. First part in this differentiation, next we'll go first part in the second pair, which is hidden by the dots. And last one is the first part of the last pair of differentiations. And now differentiations of the pairs of differentiations. You can recognize here the dot product of the f dash bold f function. I mean, what I'm saying is this actually. You can recognize here in these components the dot product of f dash and g, and in these components of f and g dash. And that's the finish of the proof. That's the right hand side here. Any questions?
Why are we changing between T and A?
Why we're changing between T and A?
Well, okay. So I understand, like, so when you put the T equals A there, but then in the next line you should either be consistently A or consistently T.
That's right. This is just a typo. Well, that's a good observation. And here it's a typo. I mean, that's a typo, of course. It's supposed to be A. It's supposed to be A. Thank you. This one's supposed to be A. Thank you very much. So here we differentiated. That's why we kept the T. And then, I mean, like you should realize it's like, I mean, right now everything is correct, and where you write T and where you write A, it is important, and it just shows the level of your understanding. So be careful here. I mean, when you apply the dash, T must be in because you differentiate with respect to the T, but then you compute the derivative at the point, and then you can replace T with A. Something like this. Any questions? Well, if you don't have any questions, let's just go to my to my main slides. Well, I think that's all you need to know from the computational point of view. I have a few slides which discuss geometrical meaning of the derivative, which is more like a demonstration side of the, it's not so much argument, but just a demonstration or understanding what's happening with the derivative. Basically, derivative of a vector function, derivative of the function of this type, when you take one variable in a domain and multiple variables in a codomain, geometrically, this represents the tangent vector. So when you compute a quotient of this type, the quotient of this type, I have this little diagram. So if this black dashed line is the trace of your vector function, when you compute a quotient of this type, f of t take f of a by t take a, it will basically be this red vector. Well, not exactly right. The red vector is the difference between f of t and f of a. But when you scale it with the t take a scalar, it will be a little bit longer or a little bit shorter. Basically, it will be longer because when t approaches to a, t take a becomes a small number. The reciprocal of that will be larger number. So basically, you're stretching your vector. So your red vector, which is ft take fa, it will be shrinking as you push your t to a. But the quotient, if the limit exists, it will stay relatively stable. It will stay stable, as a matter of fact. That's the requirement that the limit exists. And eventually, when t approaches a, this vector will give you the direction of the tangent line. And so geometrically, you can use this number, which you can compute algebraically by using the preceding two theorems. You can use this number to predict or to calculate numerically the tangent line to the curve given by the function f. I have this, I put some effort into actually animating this push with this movement of the point t to the point a. Look at this. So it's the same diagram. So that's exactly that's what happens when you're pushing your t to a. Your red vector, it's shrinking because t comes closer to a, f of t becomes close to f of a. But because you divide this by another small quantity, t take a, the direction of this red vector, it will very often become stable, and it will just fix, or eventually it will show you the direction of the tangent line, like this. Like this. It's one of the interpretation of the derivative of the vector function. The other interpretation is the mechanical one. Both of them, there are questions in the tutorial set. You will see the tutorial set soon, which exploit both of the interpretation, geometrical one and the mechanical one. Mechanically, derivative is interpreted as a, here it is. Mechanically, if you treat your vector function as a position function of a particle which moves, and on that occasion normally people use the r letter for the name of a function rather than f, it's just a convention. So if you interpret your vector function as a position of a particle, then the derivative given by the limit, if it exists, it gives you this direction and magnitude of instantaneous velocity at the particular point. You can step it up a little bit if you differentiate the velocity function. That will be the acceleration or instantaneous acceleration of that particle in that point. And I think it's, again, the limit itself self-explanatory in this regard, because the difference between r of t and r of t naught is just the displacement of your particle. When you divide by the time required to produce that displacement, that's the average velocity. When you push your time to t naught, you end up with the instantaneous velocity. And the same with the acceleration. It's pretty much informative slides only. As a background required to the mechanical questions in the tutorial set and the geometrical question in the tutorial set. And that's basically everything you need to know, just summarized on these two slides. Any questions? Well, in relation to curves and the derivative, I have another two, actually only one concept to discuss with you. Again, it's just a relatively shallow discussion. It's just on the level of definitions. It's the concept of smooth and piecewise smooth curves. Look how we define a curve to be smooth. We say a curve is smooth over an interval interestingly enough, we never define curve smooth at the point, unlike differentiability. Differentiability defined first at the point and then from that on the interval. With the smooth concept, you only look at the interval. So we say that the f is smooth over the interval if it is differentiable over that interval I. Well, you may accept the endpoints of the interval. And on the top of that, we also require that the derivative is non-zero all the time. This extra requirement, I will show you one example why we need this requirement. Look at this. Well, the curve is called piecewise smooth over the interval when you can split an interval into a union of smaller subintervals, finite union of smaller subintervals, such that your curve is smooth over every individual interval, but maybe not smooth across the whole union of intervals. So it may break the smoothness in the join points, but across the subintervals it is smooth. In that case, you call it piecewise smooth. It's just definition-wise. It's just definitions. Yeah. I have one example to demonstrate why this requirement is important. Why we require not only the differentiability of the vector function, but also require that the tangent vector is non-zero, or the derivative is non-zero, is the example. If you take a vector function like that, t cubed I t squared k, if you employ one of the methods we discussed 2 days ago to how we can plot this function, that's the methods. Look at this. We just denote x t cubed. We solve for t. We sub it into y, like this. You will end up with the power function. For the power function, we know how the graph looks. It's like a branch of a parabola. Not canonical parabola, but some parabola. So that's how the path of the vector curve will look. Yeah, that's right. That's exactly the graph of this function. What you can see on this example is that, do I do that actually? Yes, I do. If you compute the derivative of this function, of this vector function, by our two theorems we struggle over today, we can do it per component way. I just done it per component way. First component 3t squared, second component double t. If you compute the derivative at the point 0, it returns exactly 0. And that explains why we need this condition, derivative being non-zero, when we define a curve smooth. Because if you look at the point, if you look at the curve, what happens at the point t equals 0, we have the sharp corner, which obviously doesn't deserve the name smooth. So my curve is not smooth at this point, and that is because of this. So even though function as a vector function, it is differentiable quite all right. There's no any problem with the derivative at the point 0. The curve itself, or the path of this function, doesn't have a smooth shape at the origin, and that's why it is so. So when you test for the function to be smooth, you have to test that the derivative is non-zero, because if it is 0, you can't say much. By the way, just listen carefully. I didn't say if it is 0, it is not smooth. I didn't say so, because it's not the case either. There are examples of curves or vector functions which deliver a smooth shape, smooth curve, even though the f dash is 0. Such examples also exist. Here it is. This one, for instance. If you take this vector function, t cubed I t cubed k, if you try to predict the shape of this function, what the shape will be? What's the shape of this function? It's a bisector, that's right. Again, you can argue the same way, just introduce x for the component that will be y equal x. It's a canonical bisector, first quadrant, third quadrant. If you compute f dash for this function, it's 3t squared, 3t squared. So at the point at the point 0, it is 0. But this time, the curve obviously smooth, right? Straight line is always smooth. 0, non-zero, doesn't matter. So these two examples just goes to show you, that this condition, if you can establish that f dash is non-zero, then you can claim that the curve is smooth at the point. If you can't establish that, then curve requires further investigation. You can't make any conclusion just from f dash being 0. So here's the two examples which show you that it might be one way or the other way. Any questions? Okay. Well, if you don't have any questions, basically here we finish we finished the elementary introduction into the several variable calculus. There is still subject of visualization. I mean, we discussed it a little bit 2 days ago, and I show you a few very simple examples how to visualize curves, or curves and surfaces, especially when you can't easily predict their shapes analytically with the software. I have some further demonstration about the visualization, and that will conclude our elementary introduction into several variable calculus. After that, we can look into limits. We can look deeper into the limits. But first, let's just do a demonstration. I mean, if you look from the handouts which I put on the website, the next page says Jonathan Kress Surface Visualization.pdf. There is such a file. It collects all what Jonathan Kress put together about how to visualize surfaces in 3D. I'm not going to discuss it in class. It's a lengthy PDF. It's and rather dull and boring. I will publish that. On the website. You can enjoy flicking through that if you wish. I encourage you to do that. What I will do today, I will do basically the same. What is in that file, I will publish that file. Well, tomorrow probably, not today. I will do this almost the same, but I will do it with the GNU plot software right now, right in front of you. That will give you some experience how to play with that, and then you can duplicate. Yes.
Sorry, could you briefly introduce the software you use, the GNU plot?
What exactly you want to know?
Like, just are we supposed to know that, or?
No, you're not supposed. I mean, you're not supposed to know it. It's not a part of the assessment in this topic to know that software. It's just a good piece of a software which helps you to visualize stuff.
Because the school introduced Maple in first year,
Mm-hmm.
and I just thought suddenly that we're supposed to know this another software instead of
No, you're not required to know GNU plot. I just personally like it for one big reason. It's freely available.
That's very good. That's very good.
It's a good reason, right? That's one reason. Plus, I don't have any other reason actually.
Probably works.
If you're really confident with the Maple or MATLAB and you know how to visualize stuff in Maple and MATLAB, go ahead and do that. It's not really hard to learn that. You just Google how to plot a 3D surface in Maple or MATLAB, and you will find the answer in the few first responses of Google. So you don't have to do GNU plot if you don't like. If you can do Maple, I'm happy with that. Yeah. Was a question? No? All right. So in this file, surface visualization, Jonathan Kress, he uses this function. Look at this. So let me just take. He just basically explains how you can use the cuts and contours of different levels of lines or level surfaces to predict the shape of a curve. It's a good skill. But yeah, I'll show you this on the GNU plot. So for instance, so the function he uses there in that file is the circular paraboloid. So the function is this. In GNU plot, that's what you do. Use the splot command. You show the box over which you want to picture your graph of three-dimensional function. So, function of two variables. So my box will be -2, 2. And the function circular paraboloid is this function, x squared plus y squared. Yeah, here it is. Yeah, why not? In GNU plot, if you want to, the graph normally a little bit skews the proportions because it's just I think the algorithm behind the plotting, it just tries to use as much space as possible. If you want to keep the proportions, remember 2 days ago when we did the ABC curve, and I showed you the view from the top, there wasn't a circle, but it was more like an ellipse, just because the software skewed the proportions a little bit. we can fix that by saying, yeah, set view equal, and then replot again. That's more or less keeps the proportions. If you want more detail, I mean more lines on the curve, you can say I want ISO samples, say 50. That will make more lines and more detailed plot. Yeah, if you want to see level curve, sorry. So it's a sections of your graph by the horizontal planes. There are two ways to level. Here you just say, well, you just say the set contour. There are two possibilities. Here you can say set contour. Or you can check what the possibilities here. You can call for the help on the contour. There are three possibilities here: base, surface, and both. It means let's just try all of them. So if I say set contour base and replot, it pictures you the level curves at the base and the XY plane. It doesn't actually. It does show the numbers. Here you see different colors, and here's the value of the function f for different colors for the level curves. If you want more curves, there's a set contour param, which is say level. Say let's just say 10 levels rather than 5. So you replot. Here's your 10 levels. Yeah. Now, well, plotting the function of two variables relatively simple. It is more fun when you plot something parametrically. We can plot the same. We can plot the same circular paraboloid with the parametric setting. Look at this. I can say set parametric. Tells me that I can use, I mean, if I want to plot surfaces, I have to use u and v parameters. So let's just make a convention that u will be the radius, r, because normally when you do, actually I want to use this, the cylindrical coordinates. So u will be r, and v will be the angle, the theta parameter. So the same paraboloid. Look at this. If I want to picture this parametrically, I can do like this. U range will be say 0, 2. V range will be negative pi, pi. Now, the function, circular paraboloid in cylindrical coordinates, it is this one. Radius times cos v, radius times sine v, and u square. Look what happens. The same circular paraboloid, a different look. That's what we talk about when this is the parameterized surface. Different parameters, different looks. You can play with angles. By the way, I didn't show you what happens if you set the contour. I set contour base. You can say both. Let's just see what happens here. I don't know if you see it. It just also shows the contour lines on the surface on the surface also. What else you can do with this? You can do something like this. You can just play with the range here. For instance, you can say let's just go not negative pi, pi, but let's just go 0, pi on 2. What will happen now? What will come up on the picture when I press enter? Huh? Quarter of this hyperbolic paraboloid. Here it is. Well, actually, it's damaged the sizing a little bit. Let's just do it like that. We can fix. Let's just picture the original one. Here's the what just happened? Here's the original one. If you can pay attention, we have the range negative 2, 2, negative 2, and 2. I'll fix this in the setting like this. I say negative 2, 2 for the x range, and the same for the y range. And now if I ask for my quarter again, 0, pi, and 2, the view angle will not change. Look at this. Yeah. Here it is. Here's my quarter with the same proportions and level lines at the same time. Look what I'm going to do now. If I take now my parameterization here, and duplicated here, but shifted by half of the revolution, what will be the image now? Huh? No. Two halves, two quarters actually. So we took my red one and just spin it 180 degrees around, right? Now, last question. What happens if I just cut my radius to say like this, 1 and 2? What will be the result of this one? Shorter. We cut off the bottom. Well, we can play with this in all sorts of ways. In the tutorial set of questions for the week 1, there will be questions to visualize this, visualize that. You can do that either with a GNU plot, or if you like Maple or MATLAB, you can do with that. Are we over yet? Are we?
So you can just download this for Mac.
You can, but we're not over yet, right? Are we over yet? I understand. 5 o'clock lecture is a tough one. Any questions? Well, if you don't have any questions, thank you very much for your patience. You're free to go.